So let's look now at radicals, and we're going to sketch a given radical function, and then we're going to determine domain and range of a radical function, including higher degree functions. Before we get into it though, let's look at our definition, and we're looking at, in this form, the nth root of a. A is any real number, and n is a positive integer greater than 1, so it could be 2, 3, 4, etc. If n is an even value, and a is positive, then the nth root of a is the positive nth root of a. What does that mean? Let's do an example. Let's say n is even squared, and a is greater than 0. Let's just pick a number 4. Then the square root of 4 is the positive value 2. That's what that's telling us. If n is even and a is greater than 0, then the nth root of a is the positive root. If n is even, and this should say a is less than 0, then the nth root of a does not exist. So let's look at an example here. Let's say the square root of -5, and we know that that does not exist, and that applies to all even degree n's. We can't have a negative underneath the square root. But if n is odd, then the nth root of a, there are no restrictions. So if we have the cube root of 27, we can find a value. There's no restrictions on the a. That would be 3. We could also do the cube root of -27 to get -3. There are no restrictions on what goes under that odd degree root. So we've already looked at f of x equals root x, and we're going to do this one more time just so we recall how we actually got our points in our basic square root function. Remember, the domain here must be greater than or equal to 0. We're going to put x values in that we can easily take the square root of, and when x goes into root x, if we go f of x equals root 0, subbing that in, we'll get 0. Put 1 in there, we'll get 1. Put 4 in there, we'll get 2. Put 9 in there, we'll get 3. Now, these are then our coordinates for our basic square root graph. And we get a shape that we've seen before, just like so. Now we're going to use that same principle to graph roots that are higher order. We're going to use this to examine, and let's first do this by graphing the fourth root of x. Y equals the fourth root of x. And again, we'll do this with a table of values to start. Figure out the x and y. Remember, it's an even degree, so we must have values that are positive. We'll start with 0. Fourth root of 0 is 0. 1, and we get 1 again. And now we want to choose a number that we can easily take the fourth root of. And if we choose the number 16, the fourth root of 16 is 2. And if we go one step further, the fourth root of 81 is 3. Now 81 is going to be too large to graph on this graph, but if we had a bigger graph, we could graph it. And because we're going to 16, we're actually going to change our graph a little bit here and say instead of this is 5, we're going to call this 10. Now let's label the other graph. This will still be the point 5. And that labeling of our graph, let's put the negatives in as well. That labeling of the graph makes it very clear that we've now adjusted the scale. In the x direction, every line is going to represent 2. In the y direction, still 1. So let's plot our points. We'll be at 0, 0, 1, 1, which is going to look something like that. 16, 2. So 16's over here, and there's 2. And again, 81 is too far away, so we'll just use these 3 points and get our sketch. It's the same type of graph, just going through those points, and we'll just not put 81 in because it's too big. Well, we can do the same thing for a graph that has x cubed. So see if you can find the values to put in the cube root of x to plot the graph. Now, because we're dealing with cube root, we have to consider both positive and negative. So here's our values that we can easily take the cube root of. Cube root of -8 is -2. Cube root of -1 is 1. Cube root of 0 is 0. And we get 1 and 2. So now we can plot those points. We don't need to adjust our graph in this case. So at -2, -8, we can put a point. At -1, -1, we have a point. 0, 0, 1, 1, and 8, 2, and we get points that look like that. Now, if we do a nice smooth curve through those values, we'll see it's like we have the square root here and the square root over here. But because we have both positive and negative values, we now have a graph that the domain is all real numbers, and we have to consider that when we sketch the graph. Now, once we know the simple form of the graph, then we can actually take that graph and we can transform it using all the rules we did in the first chapter. So here is our graph. We want to graph this cube root, and this cube root, if we look at our transformation, we likely want to take this equation and rewrite it in the form that allows us to interpret the transformation. So it's the negative cube root of factor out the negative, x minus 1 plus 2 outside the square root, or the cube root in this case. Now we know that this graph has been reflected across both the x and y axis, and it's been transformed 1 unit to the right and 2 units up. So we can take our basic cube root graph and transform it. Look back in your notes if you need to get the basic cube root graph. We have those points. I'm just going to put those points in as green points like that. Now I'm not going to sketch the graph because I know those points are going to transform. So let's transform one point together here to start. I'm going to start with this coordinate down here. A reflection across the x-axis is going to put that coordinate right here. Reflection across the y-axis is going to move that coordinate, to right there. Now we're going to move this point 1 to the right and 2 up, and here is our new transformed coordinate. See if you can now transform the rest of those points and sketch the graph. And using all our knowledge from chapter 1, there is our transform graph. We have taken our original XY coordinates and we have transformed them by first reflecting the X and then moving it to the right one, and we have also reflected the Y and moved it up 2. So a variety of ways you can think about that in the transformation, but it's just using all the information we did in the first chapter to graph that new cube root function. Well, if we can graph a function, we can also determine domain and range of that function. And it is important to know the domain and range. These two we already have an idea about. If y equals root x, the domain, remember, whatever's under that square root must be greater than or equal to 0. And the range would then also be a positive number. We're always going to have a y value that's positive if we always take a square root of a positive value. The second one here, cube root, well, there's no restrictions on x. We can get both positive and negative numbers, and that's the same on y. Positive or negative numbers, no restrictions. We have to keep in mind, though, that For odd root radicals, there's no restrictions on the domain and range. It can be all real numbers. It's the even roots that have potential restrictions. So here's what we do for even root radicals. To determine the domain of an even root radical, just take the radicand and set it greater than or equal to 0. That'll always determine what the domain is. And the range, I'm going to come back and explain this range. We're going to look at an example and then bring it back to here to explain how simple it is to find the range. Let's start with this first example. Negative square root of 4 minus x plus 3. To determine the domain, we just take what's ever under the radical and set it greater than or equal to 0. And now it's just a matter of solving that inequality. We'll get negative x is greater than or equal to negative 4, dividing both by negative 1. Remember that changes the direction of the inequality, and we get x is less than or equal to 4. There's our domain. Now our domain is going to define the range. And what we want to think about when we define the range is, let's imagine we actually put the value of 4, the largest value in the domain, in that radical. If we were to put 4 in there, what we would do is we would get negative square root of 4 minus 4 plus 3, which is really negative square root 0 plus 3, which is really just y equals 3. Now that would be the value in the domain. Now that would be the value in the range for the largest value in the domain. Now let's just explore this a little bit. If we put any other number into that radical, we're always going to get out a positive number, a positive value. So if we look down at our domain, if we were to put any value in to that radical, we're going to get a positive value, and then we'd have to add 3 to it. But this positive underneath with a negative on the outside is going to result in a negative number, which means our y value for any other value in the domain except 4 is going to result in a negative radical. Now that negative radical, when we add 3 to it, is going to get a much smaller number. We're going to get smaller. Now what that can tell us is that our y values are always going to be smaller, less than or equal to 3. There's the range of this radical function. And that might seem a little complex at first, but we can go back to our notes here, and really this is the process to find the range. Take the radical, set it equal to 0. Find out what you get equal to 0. Then we take the original equal sign and you're going to change it to some type of inequality. If the radical is positive, then the y value is always going to get greater than some value. If the radical is negative, then it's always going to get less than some value. And this process can help us find the range rather quickly. So let's try it with the next example. Here's another square root. We want to first find the domain. Well, we take what's under the radical and set it greater than or equal to 0. Doing a little bit of algebra here, we'll get 2x is greater than or equal to 6, and it's pretty easy to see here, x is greater than or equal to 3. There is the domain of this radical function. Now the range, let's use that process. Well, we have a look here. The radical is positive. There's a positive value not written there, so we can take our original equation and say it's going to be greater than or equal to, if we take our radical and set it equal to 0, we're going to be left with a minus 2. So it's actually quite straightforward once we get that concept to see that y is always going to be greater than or equal to negative 2. So just as quickly as you can find the domain, you can find the range if we use this process. And we're going to continue to look at more examples like this in class.